Hello, good afternoon everyone. Welcome to the class ECE341, the probability and stochastic process. Today let's keep working on the examples last time we studied, right? Okay, this is ECE341. This is for the 13-week Fridays class. Okay. Last time we studied one process is x of n, which is a IID Gaussian process. IID means independent, identically distributed, and they are Gaussian. So all of them, x of n, will obey Gaussian with mu and sigma square as a parameter. Okay. So we have these. Then we have studied the function f x of n. The PDF, if we have several, and 2 until x of n m, then x1, x2 to xm, right? We give the function of this kind of, we give the function of these two cases, right? Yeah. And we also have something we know. X of n, this process, it is a stationary process, as well as the y-sense stationary process. And we also know those average values. Mu x of n, it is just mu, just this constant. And Cx of n and m, it will be, let me see, it will be sigma square or 0. Here's if m equal to 0. Here if m do not equal to 0, right? So we have this. And what else do we have? We also have that one, Rx of n and m. That will be sigma square plus mu square if m equal to 0, and it will be just mu square if m do not equal to 0, right? So these, what else do we have? Okay, doesn't matter. If you want to find more detail, you can go back to last class. All right. Okay. Today we consider some changes on x. We build two process based on x. We let y of n equal to which one I gave last time? I think it's this one, right? 2 of x of n plus 3 of x of n minus 1. This is the process. The yn is a different process, right? We already have x. Now I define a different process. The y of n is given by this. And another one, z of n. It is also 2 of x plus 3 of x, but the index is different. Here's 2n, and this is 3x of 2n minus 1. Now we want to study these two processes. We want to know more details about them. Okay, so yeah, which one? We studied z firstly. Okay, consider z firstly. Consider z of n. Z of n is obtained from x, 2n, and 2n minus 1. So the things like, if this is n, I use, this is a z of n, z of n for n, and here we have z of n. This is random variable, right, at the time n. And what is z of n? It is summation of x of 2n and x of 2n minus 1. So these two combine together. 2n I need times 2, and 2n minus 1 I need times 3. Then do a summation, I have zn. Then next z will be what? Z of n plus 1 will be how to get this value. It's similar, right? It will be these two values, x of 2n plus 2. Here's times 2. And here's x of 2n plus 2 minus 1. So 2n plus 1. Here's times 3 to summation. We get z of n plus 1. So you can see we have sequence x. Now I pick 2 to summation with some weight before the summation. I get z, and I use another 2. I do the same operation times some constant to summation. I have next z. So by this way we can have z. And we know x is an IID distribution, right? So all of them, they are independent. They have same distribution with the relations are independent. Now these two I get z, and these two I get z n plus 1. So obviously they are independent, and they have same distribution. Make sense? Yeah. This is a summation of these two. This summation of these two, and all of them, they have the same distribution. So you use these two to get zn, and use another to get zn plus 1. They should have same distribution because these are same. Okay, so we can know z of n is also IID, right? Independent each other, right? They are independent each other. They have same distribution. All right. And okay. So if you just look at like here, you know, z of n is also an IID. Then what is the distribution of z? Then you need to remind you something. Do you remember we discussed the Gaussian process before we go to here? We have discussed the Gaussian distribution, right? Gaussian, multiple variable Gaussian. And in that case, we know like this one, I have two independent variables, each are Gaussian. Then we do summation, it is still Gaussian. We do the summation or times a constant, it is still Gaussian. So this is also and Gaussian. Yeah, we can have this one. Then what is the distribution? What is the density function? Right? You say Gaussian. Then what is density function? Or in other words, what is the parameter? What is these two parameters? For Gaussian distribution, you always should know what are these two numbers, right? You want to know these two numbers. What are these two numbers now? Okay, these two numbers for z, we have this. The E of z. Actually, it's I use a random process, stochastic process. I use notation this one. Mu z of n. This one, actually, this is a expectation value of z of n. What it is? Alright, just plug in. This is a 2 of x of 2n plus 3 of x of 2n minus 1. Okay, this is the definition of z. Z is defined by this way. Okay, then it is 2 of e of x of 2n and plus 3 e of x of 2n minus 1. Alright, now each one they are Gaussian with each one, all the x obey this distribution, right? So the mean should be mu, and variance should be sigma squared. So here we use a mean, so 2 of the mean mu, and another is 3 of the mean mu, so totally 5 mu. Now we know the mean of z is 5 mu. And the second constant, we want to know the variance. Actually, we can have the variance. Variance, I use this notation, sigma square z of n. This one will be this. There will be e of z of n squared minus e of zn squared. Right? The variance of z. Variance of z should be this one. Okay. Then how to calculate? I need a plugin. Okay, I need more space. Anyway, z is 2 of x 2n plus 3 of x 2n minus 1 squared. Right, this is zn. And minus, okay, e of zn we already have is 5 mu. So okay, just minus 5 mu right here. 5 mu times 5 mu times mu is squared. Okay, then we calculate this first term, sigma z square of n. That will be okay. Square of this term is 4 of e of x 2n with a square. Okay. And then combine these two together. It's 2, 3, 6. 6, 2, 6 is 6, 12. 2, 6 is 12. 12 of e of x of 2n times x of 2n minus 1. Right. And then plus 3, there will be 9. E of x of 2n minus 1 square. Then take e. And minus 5 mu squared. Okay, so we have this one. Then what is this? Okay, this one we know this is just the e of x squared, right? So this will be variance of x plus ex squared. Can we get this? Yes, right? Variance should be ex squared minus e square of ex. So I move that minus this term to the right side. So we have this formula. Okay, and this one, we know they are independent, right? So this will be just independent. We know they are independent. So they are just we can separate them as two pieces, right? Summation of 2, summation of the e of each. Okay. And this one, okay, this is also square, x squared, right? So still that one. Okay, now we can have, this is 4 of, this one is variance minus square of e. So variance will be sigma squared, and that one will be mu with a square. This is ex squared. And then 12 times e of first and e of second. Then both are mu, so just mu squared. Okay. And this one is 9 plus 9 of these. This is same with this part. So 9 of sigma squared plus mu squared. And minus 25 mu squared. Alright, so what it is? For the sigma square, I have this one sigma square, this one sigma square, so I have 13 sigma square. And the mu square, I have 4 plus 12, right? 4 plus 12 plus 9 and minus 25 mu square, right? 4, 12, 9 and negative 25. Okay, so this is 13 sigma square. This cancel, right? This is 16 plus 9 is 25. So this cancel. This okay, just this one. So we have the variance. Variance is just this one. All right. By this we can claim z of n, where obey the normal distribution with variance with expectation value is 5 of mu and the variance is 13 of times sigma squared. So we have this z of n, this one. Alright, for z of n, now we are clearly know what it is. Z of n is IID process in independent identically distribution. With the Gaussian is just this one. Mean is 5 mu and the variance is 13 times sigma squared. So this is Z of n. Z of n. Right. It's your IID. Then from IID, Z is IID process, so it is also stationary. It is also stationary. And of course it is also y-sense stationary. So we have all of this. This is Z of n. Z of n. Alright. Now let's consider the second one. Second case. Now consider y of n. Y of n is defined by 2 of x of n plus 3 of x of n minus 1. Now we have to like this. Okay, similar. How to get this one? You can use a graph to see the relation. This is y of n. It will be a combine of 2, right? This is x of n. This is x of n minus 1 times 2 on this and times 3 on this. Do summation, we get y of n. Then next, y of n plus 1. Where did it come from? It will come from 1 is x of n plus 1, right? Here's y of n, here I have 2 of x of n. So here's y of n plus 1, I have 2 of x of n plus 1. Right? And then need 3 of n minus 1. Now n is n plus 1, so here will be 3 of xn. 3 of xn. So this one times 3 to summation, I have y of n plus 1. And if you want to try more, this is y of n plus 2. It will be summation of x of n plus 2 times 2 here, and this one times 3 to summation, I have this term. Okay. We have relation looks like this. Okay, you see, these two, they dependent. Right? They have a common part, so they are not independent. They are not independent. Similar, these two, they also have some kind of relation. They are not independent. But these two, they are independent, right? Y of n is combined of these two, and y of n plus 2 is combined by these two. If you consider more, like y of n plus 3 and so on, all of them, they are independent with y of n. Similar, we have this side. We have another one. This is y of n minus 1. This times 3, 2, this times 3 to summation. Then you see y of n minus 1 and y of n, they have a common point is here. So z are not independent. But when the negative minus 1, you consider minus 2, they go more in the negative direction, then that one minus 2. This one and y of n, they were independent. Right? Makes sense, right? Independent. This one will be combined of these two elements. So you compare with y of n. These two, they should be independent. Okay. So this time we will see the y of n is not an ID. Y of n is not an IID process. ID process. Alright, because they are not independent of each other. These two, they are dependent, and these two, they are also dependent. Actually, every two element, if they are just neighbors, the index just has one difference, then they will be not independent. Okay, so this is not an ID, not independent. And whether it is identically the distribution, do we have the same distribution? I will say yes. Actually, we can calculate similar ways z. Each y of n is summation of these two, so we know y of n is a Gaussian. Let me write it. Y of n equal to 2x of n plus 3x of n minus 1, and xn and xn plus 1, they are same. They obey the normal distribution with mu and sigma square. For all the n's, we have these, and they are independent, right? ID, right? The ID, so the I is independent. And the second I means the identically distributed. Identically distributed, so they have the same distribution. So the world looks like this. This is this is x. X is this one. They are Gaussian and ID. So we can have y of n is Gaussian. We have this one. They are Gaussian. But they are not independent anymore. Y of n and y of n minus 1, they are not independent. But of course, if they have long distance more than 1, y of n and y of n plus m for any n m larger than 1 or m smaller than negative 1, smaller than negative 1, minus 2 or even more, like this. Z and these, for this case, they are independent. Alright, you got it? Yeah, just like this one, right? Like y of n minus 1 and y of n plus 1. These two and these two, they are separate, so these two, they are independent. Now the difference between these two indexes is 2. And when the difference between indexes is 3, we consider these two random variables, they are also independent. Okay. So here's when you check the difference, this index n, this is index n plus m. If m is 0, of course they are same thing. If m is 1, that is the case, they are neighbors. They are dependent. And when m is larger than 1, of course another side is smaller than negative 1, then they are independent. They are independent. Right. Okay. So we can claim y of n is not IID process. But y of n is stationary. Why is it stationary? You can see the distribution of y. You know, when you move for different y, different n, they have same distribution. This is for single one. If you consider pair of them, you pick any pair, you move it along this n-axis, the distribution should be same, right? Yeah, you consider 2, you move them, the joint distribution should be same. So this is a stationary. And then we can also say it is y-sans stationary. Because it's stationary, so of course we know it is y-sans stationary. So we have y satisfies this trait. It is not ID, but it is stationary as well as y-sans stationary. Okay, then we want to know those average values. Of y of n. The first one we consider the mu. This one that means expectation value of x of n. But we know x. Oh no, sorry. I want to find y. We know x is we know y is a summation of 2 of x n plus 3 of x of n minus 1. And we have this one. Then I separate it. So similar with previous calculation, we will have 5 of mu. This should be 5 of mu. Okay, this is the mean of it. Then the covariance C. Second one, we consider the C y of n and m. We consider this one. This one for z, for previous example for z, because this is IID. It is IID, then we can have C z of n and m. This will be 0 if m do not equal to 0. And if m equal to 0, C will equal to the variance. C is just the variance. Alright, so this is for z. Because it's ID, so we always have this kind of data. But for CY, CY is not ID. Right? Y is not ID. So we need more details to calculate. So what it is? Okay, by definition, this is a covariance of y of n and y of n plus m. This is the cy of n and m. Then this will be e of y of n times y of n plus m minus e of y of n times e y of n plus n minus 1 n plus m. Okay. All right. And now we have 3 cases, right? With 3 cases. When m is larger than 1, now m is 0, they are same. M is 1 or negative 1, they are, they are neighbors, right? They are neighbors. These two, right? Y of n, it is a neighbor with y of n minus 1 and y plus 1. For both of these two, they are have common part with y of n, right? So these two, they are not independent with y of n. They have some common information coming from x of n and x of n minus 1, right? If the difference between the index is like 2, n and n plus 2, or n with n minus 2, or even more, then they are independent. So here we have 3 cases. The first case, the m is 0. M is 0, then these two are same. The m is 0 is a positive or negative 1. They have 1 difference, right? and otherwise. That means m is not 0, is not 1, is not negative 1. Okay, otherwise we have three cases. For first case, m is 0, then these two are same. These two are same, right? Y of n, y of n. Here is also same. Then it is e of y squared minus ey with square. So this is the variance of y. So when m is 0, this is just the variance of y. Y of n, right? It's this one. And the variance, I think I just do we have that? Oh, I will calculate later. Okay, this is when they are n is 0. Okay, when m is positive or negative 1, I need a minus. Or is it minus? When m is positive or negative 1, then they are related. We cannot use the okay, I need to calculate. I write it. E of y is y of n and y of n plus or minus 1, right? So this case, and the minus here it doesn't matter what is n. This will be 5 mu, this is another 5 mu, so it's always 5 mu with a square. And otherwise, this case they are independent. Otherwise they are independent. When they are independent, this one will be equal to e of y times e of y of n plus 1. Right? So this is e of y of n times e of y of n plus 1, n plus m. I don't know what is m. Now m is not 0 in the positive and negative 1. And minus e of y of n and e of y of n plus n. Okay, it is just this part. Okay, what is the variance of yn? Okay, I will do some calculation. Variance of yn, it is variance of 2x of n plus 3 of x of n minus 1. So this is a 2x of n, and I can move 2 outside. But for variance, I need a 2 square. When you move a constant outside, you need a square. The variance of x of n, actually it's variance of x, right? So this will be sigma squared. And plus, this will be 3 take it out, that will be 3 squared. Then variance of x of n minus 1, that will be sigma squared again. So totally 2 is 4, 3 is 9, 9 and 4 plus 9, that will be 13, right? 13 sigma squared. This is variance of y. And the second here, we need to calculate this one, e of y of n and y of n plus or minus 1. This one. For this one, we need to plug in what is x, what is y. Y is 2 of x plus 3 of another x. The index is like this. And the times, oh, I need more space. I put it here, right? Times y will be 2 of x of n. Now n is n plus or minus 1. And 3 of x of here is n plus or minus 1 minus 1 more. Right? Like this. Alright. This one times this one. And take mean value. Look like this. Okay, this is the wrong one. And this will equal to this one times this one. I get 4 of e of x of n times x of n plus or minus 1. Okay. this one times this one, and then plus this one times this one. This is 6 e of x of n minus 1 and x of n plus minus 1, just like this, right? One more, okay. And the third term, this one times this times this, the first two. Okay, now this one times this one. So it will be 6 e of x of n times x of n plus minus 1 minus 1. And then last term plus these two times together. That should be 9 of e of x of n minus 1 times x of n plus or minus 1 minus 1. Then we have this. Okay, so what is this one? We check the first one. This one, they are different, right? The index, no matter he is a plus 1 or minus 1, these two indexes are different. And we know x is ID. X is ID and Gaussian. ID and Gaussian. So they are independent. Then I can calculate the expectations respectively. And each one is a Gaussian with n of mu and sigma squared. So the E of this is mu. E of second one is also mu. So here is mu squared. So 4 and mu squared. And this one, now we have two cases. If here is a plus 1, they are different. If this is a minus 1, they are same. Okay. And okay, I check this one. Do we have single case? This one may be same or not equal. Okay, this one, this one, they are always different, right? This is n minus 1. This is n minus 1, then plus or minus 1. So these two index should be different. Then we have similar with that one. There will be plus 9 of mu squared. Okay, this one give this. This one give this. And these two, when this is a plus 1, these two are different, and these two will be same. You see, when this is a plus 1, so plus 1 minus 1 is 0, just n. This is also n, xn, xn, right? So when this is a plus 1, these two are same. These two are different, these two are same. And if this is minus 1, these two will be same, this will be different. So no matter here is a plus 1 or minus 1, if you combine these two together, you should know one of them will be squared. It's a e of x squared, and the other will be they are different, independent, different. They can separate, right? We always like this. So these two I can write as 6 of, like if these two are same, if these two are same, that is minus 1. If minus 1, these two are same, this will be e of x squared. So this is a e of x squared. Because the ID is coming from x is this one, right? Yeah. And when they are same, this is ex squared. At the same time, these are different, so this will be ex squared, like this, right? So these two, one is this, one is this. Depending, if this is a negative, then this is this one. If this is a positive, then this will be this one, and the other will be the other one. Okay. Then this is, okay, so this one will be sigma squared plus mu squared, and not sigma 2. And this will be mu squared. So I can add all of them together. What it is? This is a 4 mu squared, 9 mu squared. This is 13 mu squared plus 6 sigma square plus 6 mu square plus this is another mu square, 6 mu square, right? 6 mu square. Oh, there's a lot. So totally I have 25 mu square plus 6 sigma square. Oh, am I good? This is we want to calculate this one, right? EY times y, this one. Okay. Alright, this is the second part. This part. Then can we get the final answer? Okay, now we can get the final answer. So we have CY of n and m. This is somehow long. So you have a chance, like a risk to forget what are you doing now. What I'm doing. I want to find this one, right? Okay, I have three cases. First case, m is 0, it is just this one. And this one we get, it is 13 sigma square. Right? 13 sigma square. This is the case if m is 0. And the second case is this one minus this one. And the first term, this part, is here. And we calculate it, we get this one, right? Get this one. This is a 25 mu square plus sigma 6 of sigma square, and minus this. This will be 25 mu square. So minus 25 mu square. Okay, this can be cancelled, right? Here's a case m equal to positive and negative 1. And otherwise, what it is? They cancel, right? These two, the same, right? yn plus m, yn plus m. Here's a minus, so they cancel. Okay, it is just 0. This is 0. Alright, so we have cy. Cy, it looks like this. Cy in m looks like this. Here's a 13 sigma square. And these two cancel. Here will be 6 sigma square. Here's a 6 sigma square. This is m equal to 1, m equal to 0, m equal to negative 1. And then all the other m's, they're zeros. So we have a graph of cy of nm, looks like this. The value only depending on m. Doesn't matter what is n. Alright. So we have this one. This is cy. And what else can we have? Okay, actually we have variance, right? Did I calculate the variance? Variance I calculated. Variance is just this one, 13. This will be variance. We have this. The variance of y of n will equal to cy of n and 0. When m is 0. When m is 0 is 13 sigma squared. And the variance is also 13 sigma squared. Right? So we have this one. Actually, we can have this for any process. Any process, this should be this one. Any process, these two are same. This is a formula for any process. And for any process, we can have this. All right, and we can also have ry of n and m. This one is auto correlation of the process x of n. Now we have name looks like this. Actually, we have this capital R before, right? We just call it as a correlation. Now, when you have a random variable, when you have two random variables, you have correlation. Now for the random process, for the stochastic process, we call this as auto correlation. Auto correlation. We add an auto in front of it. This one will be E of y of n times y of n plus n. Right, it's this one. And actually I have it. Right? Do I have it? Yeah, it is just this part, right? This part, so it will be this one, and yeah, the before this one, right? Okay, so we can just apply it. If I want to know this one, it is this one. Then it is also 3 cases. M equal to 0. It will be this one plus this one, right? This one plus this one. And this one we know is a 13 sigma squared. And these two is a 5 mu. Yeah, actually this one, right? It should be 5 mu. So it's a plus. This one will be this plus this. So plus 5 mu squared. Okay, this is it. M equal to z. M equal to 0. Well, M equal to positive or negative 1. So this one will be and it is this one, and we calculate, we get this. It's this one. Okay, so it will be, I put sigma square, it's this one, I put sigma square in front, 6 of sigma square plus 25 mu square, if M is positive or negative 1. And otherwise this term, otherwise is here. Otherwise should be this one, right? Oh, I didn't calculate. I say they can cancel. Oh, yeah, it's fine. It's a 5 mu, just 5 mu square. Yes, 25 mu square. It's this one. So we have the autocorrelation, and we also have this one. I didn't give the answer. Answer is here. Yeah, this one. Actually, we have name. We call this is autocovariance. Covariance of the process y of n. Okay, we are done. We finished calculate these two random process. We know a lot of things about it, right? We know it is whether these two, one is ID, right? One is ID Gaussian. The other is Gaussian but not ID. It's just stationary. And both of them, they are y-sense stationary. And we can have the autocorrelation, autocovariance, and they are mean. I got both means, right? Yeah, I have mean, right? Mean of it. And I also have mean of y. Oh, sorry. Where's that paper? It's a mean y is here. Yeah. Mean of y is here. Alright. Okay, that's all for today. And see you next week. Right? This is Friday, so have a good weekend. Bye bye.